Okay, so a lot of things can be modeled with exponential functions, and we're going to, over the next couple of videos, have a look at that. So exponential models and introduction is our focus on this. And we need to be able to identify exponential models and do some basic calculations using given exponential models. So exponential model, how do we identify? Well, here's a situation here. So they've done some field work here and they've looked at the mass of a virus in milligrams, and they've taken 10-minute time periods. They've broken time up into 10-minute periods. In other words, they, at the start of the monitoring, they noticed, or they weighed or detected 20 milligrams of some virus. After a set of 10 minutes has passed, okay, one time period we'll call that, so that's called 10 minutes a time period, there was 1.3 times as many. So in other words, they detected 26 milligrams of the virus. So that growth ratio is 1.3 times as many as there was. And if we see that pattern repeated over the same increment in time, if that same growth ratio, which is a multiplier, happens, we have an exponential situation. If this is unlikely to happen, of course, but if it was adding 6 each time, that would not be exponential, that would be linear growth. So we have to check it out. We have to check it out over an extended period of time. So and the case is not 6 is being added each time, it's more than that. Apart from the first jump was 6, the rest of them are greater than that. So it's a multiplier, it's a growth ratio, and therefore we have an exponential situation when there's a fixed growth ratio. So each time we have 1.3 times as many of these viruses as last time. So we can see some patterns. It's the initial 20, that's the initial amount. Firstly, it's times 1.3, then it's times 1.3 times 1.3 from the start. So that's 20 times 1.3 squared. So it's just building on that. 20 times the previous 1.3 squared times another 1.3 is the next lot. That makes cubed, and so on. So we have an index building there. So it's clearly an exponential function. Well, what makes something identifiable as an exponential function? Yes, it's that growth ratio, but what we need is something in the form, very basically, the dependent variable equals some initial value, which might be A, times a growth ratio or a decay ratio raised to some power, which is the independent variable. And that's what we've got here. We've got, in this case, we've got the, let's call V for the mass of the virus. The mass of the virus is 20 times, now the growth ratio is 1.3, so 20 times 1.3, and let's call the time period T. And that's our model for this particular situation. So that's an easy, fairly straightforward one. And this gets used with a lot of things. Now, if we have that growth ratio bigger than 1, as we've seen in previous videos with the graphing, it'll represent a growth, some sort of exponential growth, whereas if B is, especially if B is between 0 and 1 in particular, and from the previous videos when we've graphed these, we've seen a decay type situation where it's more like that. So that would be things like the cooling, Newton's law of cooling, which you might have seen in a previous video. Things like radioactive decay. Radioactive substances have half-life and their mass declines. But growth, the growth of cells like this the virus we just saw, population, which can be quite scary, compound interest. So another example for decay would be depreciation. If you've studied geometric sequences and series, you'll see some links, except for these tend to be continuous functions, whereas sequences and series are more discrete. So to finish off, we'll do two examples which use which is called the future value formula, and it's closely linked to the compound interest formula, and it's an exponential example. And if you have a close look, you've got the equivalent to our y equals a, so the PV, present value, is a. And do we have a b? Well, yes, if b can be broken down into 1 plus I, the annual percentage increase, and we have little n is the x. So yep, we do, we have that form. So future value is what it's going to be worth in the future, some commodity or product or item. Present value is what it's worth now. I is the annual interest rate as a decimal, or the annual percentage increase. So if it was 4% per annum, it would be written as 0.04, and n is the number of years. So we're looking at this in an annual way. It is possible to look at this in a quarterly, weekly, monthly, semi-annually, fortnightly, daily manner, but we're just going to stick to annual on this one. So a house is worth $150,000 today. If it increases by 4% per year, what will it be worth in 10 years? So future value is the present value times 1 plus I to the n. Okay, we've got I is 0.04 and present value is $150,000. Where is this? Maybe this question is very old. Where is this place where you can get a house for $150,000? It's not where I live. What else is there? There's 10 years, so n equals 10. We're ready to roll with this one now, because we've got to find future value. Alright, so future value equals 150,000, 1.04 to the power 10. Grab the calculator. And I calculated that, and we got $222,037 to the nearest whole dollar. And the final example, how many years will it take a valuable painting that is increasing by 25% per year to grow in value from $200,000 to $1 million? Assuming this is constant, okay, we've got to assume that things don't change. It might increase even more rapidly if the scene goes crazy, or it might do the opposite and flop. So how many years? That means we need to find n. Okay, and so we've got I is 25% or 0.25. We've got present value is $200,000. It's worth as much as one of those houses. Alright, and future value, $1 million. Assuming it gets to it. Assuming there's no big fire in the art gallery or something. But it'd be insured, I guess, wouldn't it? Maybe. Anyway, and as we said, we've got to find n. So sub it in. We got $1 million equals 200,000, 1.25 in brackets to the power n, which is the unknown. Okay, so what we can do is divide both sides by 200,000. So we got 5 equals 1.25 to the n. Now in this video, I'm assuming you haven't learnt log law 3. You may use log law 3 on this, where you take logs of both sides and move the n, but I'm going to just use the definition of a log, because that's where I am pitching this video. So definition of logarithm. So that means we rewrite that equation. So basically, log to base 1.25, provided you've got a calculator that can do that, or you know the change of base rule. Log of 1.25, sorry, log of 5 to the base of 1.25, more correctly, equals n. And we get our calculator. n equals 7.21 years. So to rise fivefold in value, it'll take 7.21 years, or about 7 years and 77 days. By the way, if you do know log law 3, that's how you would do it using log law 3. Take logs of both sides, move the n to the front, and divide through, and you get 7.21. If you don't know that, just stick with the definition of a log.